Hi everyone, welcome back. So in this video, hopefully it'll be a quicker one for you. What we're going to do is just briefly talk about rotational kinetic energy and different ways that it might be used in a problem. Okay, so here we go. Rotational kinetic energy. Right? The equation for it is your K for kinetic energy equals 1/2 I omega squared, where I is your rotational inertia and omega is your angular speed. Right? If you think back to your translational, your linear energies, the kinetic energy is 1/2 mv squared, mass times speed squared. Well, if you remember from earlier, your rotational inertia is the rotational analog to mass. Your angular speed is the rotational analog to speed, right? So it's basically the same question, but now we're using rotational terms instead. Now, there really isn't much else different about rotational kinetic energy. Its unit is still the joule. We still use it in the same way. But if you are being asked a question about this, it's important to keep in mind there are a few different ways they can ask you about it. The first thing would be, let's say you have just an object, a disk maybe, and that disk is stationary. It's connected to a table or something. Could be a turntable for a record player or something like that, and it's just rotating right along, right? You calculate its rotational inertia, or maybe they just give it to you. You calculate, or they give you your rotational, your angular speed, 1/2 I omega squared. Cool, not really much different there than anything else. Now, of course, with physics, we don't just leave it at its simplest possible solution, or simplest possible scenario. Let's say, for example, you have a ball, and that ball is rolling along the ground. Okay, so what's happening is you have the ball moving through space linearly, translationally, but at the same time, it's rolling. Okay? Okay, so here's our V for our translational speed. Here's our omega for our angular speed. Right? How would you calculate the total kinetic energy for this object? Well, you'd have to take both into account. So what you would say is your total kinetic energy equals 1/2 mass times speed squared, which takes care of this component, the translational component, plus 1/2 I omega squared, which takes care of the rotational component. Right? So the total kinetic energy would be the sum of these two things. Luckily, energy is scalar, so it doesn't really matter what direction any of these things are going or how it's rotating, right? We're just looking at the values, adding them up. Okay? And another common way you can look at it is, let me just kind of erase so I can draw, something where maybe it's like a roller coaster, right? It starts up kind of above the ground and then kind of comes down and around and so on and so forth. Okay, so maybe the object is up here to start, okay, at some height above the ground, and as it's coming down, it's going to roll, right? A lot of times, you know, before we've gotten into rotational motion, maybe it was a block that just kind of slid along, right? But if we're talking about an object rolling, usually they'll say without slipping, which means you know it's going to roll nicely the whole way through. You're going to start with gravitational potential energy, and then once it's start rolling, it's going to have that rotational kinetic energy and some translational kinetic energy. Right? So this could be a conservation of energy question. Right? So how would we handle this? Well, I'm going to do E sub t, which represents the total energy of any given system. Okay? Now, that will be your gravitational potential energy for whenever it's above ground level, plus I'm going to do K sub t for its translational or its linear kinetic energy, so as it's kind of going this way or up this way. And then I'm going to do a K sub r for its rotational kinetic energy, so as it's rolling along the track. Conservation of energy will say that this total energy will be the same at any point. So if you were to compare here to here, for example, well, here it's got some height, so you're going to have some gravitational potential energy. Is it moving, rolling, whatever? If so, then you'll have terms for this. If it starts at rest, then you won't. And then at different points, you'll be able to calculate things based on any information they give regarding this. Okay? So bottom line is rotational kinetic energy is just another term that might show up in a problem regarding conservation of energy, work, power, so on and so forth, right? These terms and these definitions are still the same. Work is still a change in energy. So it takes work to cause an object to start rotating. Power, how quickly is that work done? Work over time. Same ideas, but now we just have this rotational kind of bit to it. Beyond that, there really isn't anything too groundbreaking regarding rotational kinetic energy, so I will leave you there. Have a good day.